Now that we know how to compute surface integrals, we're ready to take Green's theorem and sort of pop it out into 3 dimensions. So first let me review for you what Green's theorem says, at least the first part of Green's theorem. You've got a vector field in the plane, and you've also got a positively oriented curve, C, that is enclosing a region, R, in the plane. Positively oriented means that if you travel along the curve in that orientation, the region is always to your left. And what Green's theorem says is if you compute the circulation of the vector field along the curve, so it's sort of like capturing the components of F that run tangent to C all the way around, then that gives you the same answer as computing the curl of the vector field across the entire region. So I'm not going to draw the vectors of the vector field. I'm just going to kind of draw some images that help us capture the statement of Green's theorem. If you go along and you sort of sum up all of the rotation that the field has across the region R, Green's theorem says that that's the same result as sort of adding up all of the circulation along the boundary. And if you sort of artificially imagine the vector field F as being a 3-dimensional vector field, so this is all occurring in the plane, but like if you just tack on a 0z component, then you could imagine the vector field as being a vector field in 3 dimensions. Then our notion of curl of F, which of course is del cross F, when you extract the k components of that, then you're just getting the expression partial n with respect to x minus partial m with respect to y. We saw that back in the curl and divergence section. So I mention that because Stokes theorem, which is what we're studying in this section, is exactly this same statement. We just allow the whole vector field and region and everything to pop out into 3 dimensions. Let me draw what I mean. So you have to imagine having a vector field, and I'm just to keep things like separate, I want to give the components of the 3-dimensional vector fields different names, P, Q, and R, let's say. So you imagine this vector field in 3 dimensions, and you imagine having a surface like this, and we're only going to be dealing with oriented surfaces, so there's some imposed like side to this surface that we prefer. So let's suppose that my surface is oriented in such a way that the normal vectors go up, right? Then around its boundary, you're going to have a closed curve, kind of like the curve that encloses this two-dimensional region in Green's theorem. So we'll call that curve C. And you could compute, of course, the circulation of this 3D vector field along the 3-dimensional curve. We've done that before. We've done line integrals of vector fields in 3 dimensions. So what Stokes' theorem is going to say is if you instead compute a surface integral of what? Well, compute a surface integral across the surface of the curl of this vector field. So the curl of this vector field is a vector field in its own right. Again, grad cross F. And if you sort of run along the surface and sum up all of the circulation of that vector field against points of the surface, then that would be a surface integral of a specific vector field, and Stokes' theorem says you get the same result. The total curl of the vector field across the surface is computed as a surface integral, ends up coinciding with the circulation of the vector field across the boundary. So let's take a look at that. Here's a statement of Stokes' theorem as promised. The circulation line integral is identical to the one in Green's theorem. It's just that we have a 3-dimensional vector field instead of a 2-dimensional one. And then the surface integral quantifying all of the curl across the surface is given by this. Okay, I realize I need this to be the surface S, not R. Yeah, so this is a surface integral over a surface S. Okay, so what I want to do in this video is prove a special case of Stokes' theorem. So I'm going to choose a vector field and a relatively simple surface, all in the abstract. And I'm going to try and give you the main idea why this line integral of circulation should coincide with the double integral of curl. And along the way, if I ever encounter a line integral in the plane, I can invoke Green's theorem that it would be a double integral of the curl of the two-dimensional vector field on the plane. And that ends up happening towards the end. Okay, so let me go ahead and then set up a simplified situation, and the way I'm going to prove this is similar to how I proved Green's theorem. I'm going to deal with the left-hand side of this equation and deal with the right-hand side of this equation separately, and notice that I can reduce them down to the same double integral. Okay, so the special situation that I'm going to suppose here is that my oriented surface is actually given by a function. That'll give me a real easy way to parameterize it, but we're still going to get the spirit of the theorem even in this simplified situation. So I assume that I have this surface, and the surface itself is a nice continuous function with continuous second partial derivatives. The vector field that is in 3 dimensions has all continuous second partial derivatives and so on, all the good things that you need for, like when you want to take line integrals and double integrals and things. Okay, so there's my surface, and the boundary of the surface is going to be called C. The orientation of the surface S is supposed to be sort of consistent with C in the following way. We call, I should have mentioned this in the previous statement, but when we say C has positive orientation with respect to the surface S, what we mean is the oriented surface S has a preference for side. So let's say it's pointing like this. C is then oriented in a right-hand rule fashion relative to that normal vector. So if you traverse the curve C in a positive orientation and you're sort of standing upright along with the normal vector that's giving the orientation to S, then the surface should be to your left each time. So it's sort of like right-hand rule-ish orientation that I have here in the image. Okay, so what I'm saying is I've got a surface, I've got a positively oriented boundary curve C, and down in the xy plane, I have what will be the parameter space. It's just the region in the xy plane that is giving rise to this surface up here. And so if I look at the boundary of that region in the xy plane, that two-dimensional region, I'll call that curve C1. So you can see the curve C is hovering directly above the boundary curve C1 in the plane, and then the surface is hovering above this domain we're calling D down here in the xy plane. Okay, so that is the setup. Let me take a look at the right-hand side of the theorem. And again, this is a S here, surface S. I want to take a look carefully at the surface integral of curl and get it down to a particular situation. And I need to give some component names to my vector field, P, Q, and R. Okay, so the first thing that I'm going to do is just inspect curl. So you remember from the curl and divergence section that you can compute the curl by computing del cross F. And I'm just going to write down what the curl ends up being. It's a vector field in its own right in terms of the partial derivative functions of the component functions. So we don't typically memorize this as the curl of F. What we do is we just set up a little matrix to compute this this cross product where del is the vector of partial derivatives. And you end up getting this right here. And then in order to set up a surface integral, I want a parameterization of the surface. And as I said, when you have this simple situation where z is a function of x and y, there's this sort of cheap parameterization that you can use. So I'm going to let the parameterization look like this. X and y are going to be the parameters u and v, and then I want to make this surface function g to match the book. Okay, so then z is a function g of x and y, so this would be a parameterization. And this is where the parameter space here is completely coinciding with the region in the xy plane over which the surface lives. Okay, so let's take a look at what r sub u and r sub v should be. And then ru cross rv, I need all this information so that I can set up the surface integral, right? And I'm just going to write, the partial of g with respect to u and g with respect to v in terms of z, just to remember, like, later I want to write the partials in terms of z, that's all. So z is a function g of x and y, so writing g sub u is the same thing as writing the partial of z with respect to x, because u and x are synonymous. And this is partial z with respect to y. So this is just a rewriting of that. My point is that the u and v were just used temporarily to get this parameterization, and I'd really like to have like everything expressed in terms of the p, q, and the r, and the x, y, and the z. Okay, so I think I'm ready to set up the surface integral now. So remember, to compute the surface integral, I'm supposed to take the vector field, which in this case is this curl vector field, and dot it with ru cross rv, which I've computed here. And then I'm going to integrate over the parameter space. Okay, so this is the double integral over the region D in the xy plane that is computing the surface integral of the curl vector field across the surface. I'm just going to multiply some things out. Before I go and work on the left-hand side of the theorem, if I just kind of write out all the terms that I see here, it'll put it in a good position for when I'm ready to match this up with the integral that results from the left-hand side of the theorem. Okay, so there you go. This is the right-hand side of the theorem. Now I'm going to go move to the left-hand side of the theorem, which is the circulation line integral, and see what I can do with it. Okay, so remember my vector field is PQR, and C is representing the boundary of the surface in 3 dimensions that is oriented positively with respect to S. Okay, so what this line integral is, as we know, is the line integral of the components of the vector function, vector field, with respect to each of the variables. So this line integral of the vector field breaks down into line integrals with respect to x, y, and z exactly in this fashion. Now, I can assume that I have a parameterization of the curve C that takes the following form. So x and y are depending on time, of course, and so does z, but I know specifically how z depends on time because z is actually a function of x and y itself. So the parameterization will then, of the curve will look like this. Okay, so using this parameterization of the curve C, I can rewrite this integral. So just thinking about it, dx, for example, is x prime of t dt, and dy is y prime of t dt. And I can use the chain rule to figure out what dz is. The derivative of z with respect to t uses the chain rule. So here's what I mean by that. Let me put it in a different color. Z is a function of x and y, and each of x and y is a function of t. So if I want to express the derivative of z with respect to t, I use the chain rule. Okay, so with this parameterization of the curve, here I'm assuming that I have time running from A to B. That allows the particles sort of to traverse the curve C entirely. This is the expression for the line integral of the vector field PQR. Okay, I'm going to rearrange some terms a little bit. So I think I'll gather the terms that have dx dt in them and the terms that have zy dt in them. Okay, now let's look at it like this. This is a two-variable function depending on x and y, and I have dx dt dt. So if I just focus on this term alone, this is an integral, this is a line integral over the curve C parameterized this way, of this function dx. And likewise with this term right here, this expression together with the dt forms a line integral of this integrand dy. And let me clarify why I am going down to C1 here instead of the entire curve C. I've expressed everything in terms of its dependence on x and y. Since z is actually a function of x and y, when I parameterize everything in terms of t, so since I have that function dependence, P, Q, and R are then only you can consider them as only functions of x and y, since z depends in turn by x and y. And so anyway, this is then the value of this original line integral in 3-dimension. It reduces down to a line integral across C1, which just depends on x and y. Now is the correct time to use Green's theorem. Let's write it in green, huh? So if we just look at it correctly, this looks like Green's theorem. This is a function m, depending on x and y. This is a function n, depending on x and y. So if I scroll up, I can see how to rewrite that. First half of Green's theorem tells me that the integral of a curve in the plane, C1, m dx plus n dy, is the curl of that two-dimensional vector field in that region in the plane. So all I need to do is figure out the partial of n with respect to x and the partial of m with respect to y. So the n and the m down here are a little bit complicated, but that's what I need to do. So I need the partial of n with respect to x minus partial of m with respect to y. That's how I use Green's theorem in the proof of Stokes theorem. So this is a double integral over d because C1 contains d as the boundary, and then I need the partial of n with respect to x. So partial with respect to x of the n function minus the partial of the m function with respect to y. Okay, and here's where things get slightly tricky, but just follow. See if you can follow this. Take the q function, for example. Q is originally dependent on x, y, and z, but the whole point of this setup is that z depends on x and y, right? So q is really, it can be considered a function of x and y only. Now, if you're going to take a partial derivative of this q function with respect to x, you got to take a little bit of care. So in the chain rule section, we know to start at the top and then follow every path down to x. So I can't just call this q sub x or something, because the dependence on z here, which in turn depends on x, is going to produce another term in the derivative from the chain rule. So I need to use this idea for q, p, q, and r when I'm taking these derivatives. This is how it looks. So partial of q with respect to x plus partial q with respect to z times dz dx is what I'm going to write for this first derivative. Okay, now I'm going to take the partial derivative of this product of functions with respect to x, and I'm going to take care when I differentiate r in the same way that I took care with q. So here goes product rule. Okay, and now I'm taking the partial of dz dy with respect to x. So that is a second partial derivative of z with respect to y, then x. Okay, so I have computed the derivative of the n function, and I've gotten these terms here. I know it's a mess, but some stuff is going to reduce in a second. Now let me do this next term in a similar fashion. Okay, we are almost there. What I want to notice now is that this term here cancels with this term as long as the g function has continuous second partial derivatives. By Clairaut's theorem, the mixed partials are the same, right? So those two terms will cancel. And similarly, not similarly, but also this term right here that results from distributing dz dy across to this is exactly the same as this term. So those two will cancel, these two will cancel, and I'm only left with the 6 others. Let me write them out. Okay, and let me then come back to the right-hand side of the theorem. This is the expression that I had developed from the right-hand side. And let's see if we can convince ourselves that these are the same integral. Well, let me underline in different colors here. Let's see if I can find. I've got a qx term, that's right here. And then I have a negative py term, that's right there. And I've got a qz dz dx, that's here. And I have, like, let's say rx dz dy, got it. And I've got a negative pz dz dy, yep. And then finally this term right here is exactly the same as that. So there you go, it's amazing, but this all boils down to the surface integral from the previous side that I promised. This is curl of f dot ds, surface integral. Okay, and there is Stokes' theorem for a specific case of surface. Just to make it easy, it was nice that I had S being described as a function of x and y. It gave me an easy parameterization. I can comb through all of this.